Good afternoon, everybody. I know it's a quite difficult task to wake you up after the coffee break and also at the end of the day, but I will give my very best first of all. Congratulations to Materialise for organizing this excellent conference, and thank you for being invited here. If you expect now a speech about how to create with 3D printing a fantastic airplane, you have to leave the room, because I'm more focusing, as the introduction was already telling you, on the real pain points which we have in production day by day. So short introduction about Airbus, but not too much. I don't think there's a need to make a lot of marketing today, but if someone wants to buy an aircraft, you can come to me afterwards. I will give you a special discount today, yes? Okay, so Airbus is a European success story. Every 2 seconds, an Airbus takes off and lands. And one point I want to highlight for you, if you see the number of aircraft sold and the delivered aircraft, you see there is a gap of 7,000 aircraft. That's our backlog. And that's the reason why we are looking for more higher productivity efficiency in our products, because if you order today, if you buy today an aircraft, you need to sell it not tomorrow, but maybe in 5 or 6 years, because then it will be delivered. So that's a issue for us, that our customers have to wait too long for our products so far. A short look on our Airbus family. Maybe you have seen already an aircraft and hopefully you were flying already in it. If not, go after the conference to the Brussels airport and then you will see some of these products. So, let's say, using 3D printing, for sure, it's a basic technology for us. First of all, due to the performance, weight performance we have to bring in. So weight is always an issue because weight means fuel. And fuel costs a lot for our customers. And if you have a look on the structure of the airframe, we have, let's say, the areas of wing and the area of the fuselage, which is bringing the big portion of weight to the aircraft. So which means here we need to focus on produce lightweight products. And secondly, cost. That's also quite interesting. Airframe makes a big portion of cost of an aircraft. And out of this, fuselage and wing have the biggest portion in the airframe on the entire cost. So we are focusing on weight and on cost, and for sure we are focusing also on the way how we can assemble in a very efficient way our aircrafts. And here I want to focus on what we are doing in Bremen, but it's an example you can put also on all the other plants in Airbus. Bremen is producing wings, wing equipping. And to give an example, we have a so-called mixed model line. We are producing the wings for A350 and for A330. And we are doing it in a flow line. And this is a tacted flow line. And the takt now today is actually 1.2 days. So that's very short takt for an aircraft wing. We have 6 stations there, and after the 6 stations, the wing is going and flying to Toulouse. So no chance to recover, which means we need parts in time and we need high level of automation. But the design of our product is in principle a very old one. And if you have a real look in my shop floor today, you see there is a lot of handmade job to do. Quite difficult to put automation in because we have not so much repeatable jobs which needs to be done. So that's one of the challenge we have in our takt. And for sure we're working here more in the area of have a kind of cobots, so collaborative robots or collaborative automation must not be a robot. And there I'm coming now through to the 3D printing, because the problem is today that all the assemblies we have to do, they are much too complex to do it by robots. And we need to come to an integrated design to have a plug-and-fly solution. And here we see a big potential for our production by using 3D printing. So it's for sure the cost, which I have told you already, for sure the weight, which I also told you, but for us it's important to produce with 3D printing manufacturing tooling, to produce also plug-and-fly solutions. So this is the benefit we see in this kind of technology today. Here you see some examples which we have already produced there. And I have to mention that we are working in Bremen because we are an Airbus group site together with our colleagues from space. So we have a common 3D printing activity there together with the space colleagues, and therefore different applications. Here you see a hydraulic component with a weight reduction potential, very well received. And here you see an old design, and we have put it in an integrated complex assembly, which is helping us for our plug-and-fly solution. So, status of additive layer manufacturing in Airbus company today. You should know that every part and every technology which is used on an aircraft must be qualified in front of the authorities. So, which means we cannot use automatically a process which is existing. So, qualification processes are running, and as it was mentioned by Materialise already, for plastic parts it was done. For material parts we are under qualification of the titanium powder bed process. We are under qualification of the hipping and the CT suppliers. Inconel is in progress, and overall we have now a common approach also for the Airbus group together with the colleagues from space to qualify additive layer manufacturing in aluminium parts. So to do so, some maybe more sophisticated solutions. Here you can see a spoiler. This is a common spoiler of an A330, which is produced normally out of composite parts. And we have done a bionic design of the spoiler, and we have produced a big part which is now under flying test. So this is a demonstration which will run next year. It's in preparation only to have a demonstrator to show that we are also able to construct and build complex parts, easy to assemble for the wing. One pain point we have still is the question of surface treatment and surface quality of the 3D printed parts. I think here is still a job to do in metallic technologies, for instance, because we see that if the surface is very rough and we have class 1 parts, which needs to sustain a very high level of fatigue, then we got in problems. Here I show you a, let's say, overall production chain, which we have now under R&D investigation to see what are the influence end-to-end to produce a 3D printed part. And to give you an idea why we have a look on it, you see here a surface built by additive manufacturing as is, and here's a surface after a special chemical post-treatment, and you see in principle, which is shown here, that you have a higher stress-resistant and fatigue behavior if you have a better surface at the end of the production. And this must be integrated for sure in the production chain of the parts where we work on heavily. So overall, and coming to a kind of conclusion, what is important for us is first of all that we need robust processes. Why we need robust processes? Because we have still the vision to have a 3D printer direct in the shop floor to print parts which are not there. So meaning if you have a problem in the supply chain, you can immediately print parts or at least a dummy part which can be installed in the product so that you can continue your takt. That's quite important, because if you have a part not there, you're moving work from one takt to the other, and this is giving us a headache day by day. Then we need very good process monitoring, which must be possible, and better surface quality, which I have mentioned already. For the manufacturing, for sure, we need low-cost processes. So at the end, it makes no sense to produce a part with 3D printing because I want to produce a part with 3D printing. So for sure, we are looking on the business case for the part. And by the way, this is also, let's say, maybe some area where we can find applications for the 3D printing because costs are higher if you have a look on spare parts. So for sure, for already running a lot of aircrafts worldwide with our customers, we have 5 spare part centers. And if there is a possibility to produce spare parts with 3D printing, this can bring a lot of cost saving in this area. We are focusing on new assembly concepts, as I've mentioned before. So plug and fly is a very important one, because we have still too much manual manufacturing in our production, and have a higher level of automation. The prerequisite is that we have a new assembly concepts. And high production robustness, for sure, as we're going more and more now in flow line production. We need robust processes, because a disturbance in the flow line can really stop the flow line, and this, let's say, makes me then a headache, or it's a pain point for me, because then I cannot deliver my wing to the final assembly line. Overall design, manufacturing-friendly fuselage structure, and also wing structure I have to mention, and lightweight design, and this can be enabled, as I've shown you, by the bionic design via additive layer manufacturing. So we see really that additive layer manufacturing is a technology for us, not for the future, already implemented today. We have a kind cooperation with different companies like Materialise, with different universities. Some of our partner universities in Hamburg and Bremen are here also today. And we are using it in all of our plants in Europe. So not only in Germany, also in UK, Spain, France. Here we have a lot of applications of 3D printing. One point I want to mention on top, because this was mentioned this morning, it's not part of my presentation, but I want to mention it here. We need to go more on digital, because then it's much more easier to implement 3D printing. But we are using also, let's say, digital technologies, Industry 4.0, for implementing a more user-friendly work environment for our workers. So for me, it's also important that we have a look on the ergonomics potential of this technology. And here also 3D printing can help us if we have, let's say, more lightweight constructions or better integrated assemblies. That's from my side. Very short. I was now much too fast, I've learned, but therefore we have more time for questions. Many thanks.
And that is really great, because the questions, they started coming in after a few minutes already. And I have to admit, ladies and gentlemen, when they introduced this tool to me, I was a bit not so happy with it. But in the meanwhile, I'm a fan, because it's really great to see all those questions coming in while you're speaking. So I'll start with the one that has the most votes yet. What sort of chemical process did you use to make your parts so smooth? And then I think they're talking about one of the parts that you showed in the...
Yeah, it was the fatigue, the slide on the fatigue. It was done by chemical milling, which we are using already today to make, let's say, proper surfaces. So it's a standard chemical milling process so far.
Okay, I hope that answered the question. If it didn't, then please react. Then another one is, how do you control additive layer manufactured products? And it says by NDT means question mark.
Yes, this is one point which is still for sure an issue we have, or not an issue, but a point which causes a lot of cost. For flying parts and flying class 1 parts, we need to check them completely via non-destructive testing. Either we do it with computer tomography, which we are qualifying for this process also in parallel, which I have mentioned. And you need really to make a kind of dye penetration if you have some cracks on it. So it's still, let's say, a big portion of the production is the NDT.
Okay. Another question, and it's funny to see, because while we're talking questions, they go up and down in the category. But traditionally milled aluminium is cheap. How is the use of additive manufacturing justified for aluminium parts?
So I think the chance we have, the opportunity we have, if we go with aluminium parts on additive layer manufacturing, is that we can change the design. So let's say to go lower weight parts, and that we can produce more integrated parts, which then can have a cost factor or cost avoidance in the assembly of the parts. So I think at the end, for sure, we need a calculation of the business case behind. But so far, we have found some pilot cases where we are convinced that we can go with cost saving if we go on aluminum parts also with ALM.
Okay, I have two questions that are about numbers. Any idea how many 3D printers you have installed?
I do not know the right number. I think it's roughly 15 only, 15, because we are not doing our parts on our own. We are working together with our suppliers like Stelia, like Premium Aerotech, and they are producing the parts for us, and I think also Materialise is producing for us.
Thank you. And the other question about numbers is, it's a funny one, how many wings per day do you produce?
Sorry?
How many wings per day do you produce?
Okay, it's what I've mentioned, the takt is 1.25, so which means every day roughly we produce one wing. One wing is leaving the Bremen plant, flying then with a beluga to Toulouse. And in Toulouse, there is a final assembly line where the wing is plugged on the aircraft. But to let you know, the wing is leaving Bremen ready to fly, which means at the end we have also a customer inspection. So meaning every day we have in principle a customer on the site. It's an airliner who's checking the wing, giving us a stamp, it's okay, ready to fly, and then the wing can be plugged on his aircraft.
Okay. Another question here is, what is the percentage split between metal and plastic additive manufacturing parts in the aircraft, but also on the shop floor?
Difficult to answer. It depends on the aircraft program we have. For instance, for the A350 program, we have a 50-50 split about composite and metal parts on this aircraft, a little bit more than 50% on composites. Including the plastics. On the older aircraft programs like A330 or A320, we have much less composite parts. It's below 40%. And from 3D printing, today, most of the parts we are using in practical applications, so meaning being qualified and flying, they're coming so far from plastics. So I would say 80% and 20% are coming in the metal side, but for sure we are improving the metal side. And if you have seen, and maybe you remember one slide which I've shown to you, the status of the qualification of the processes for the titanium. If we have, or if we would be successful this summer to get the qualification stamped by the authorities, so agreed by the authorities. I think the parts related to metal and coming from titanium being 3D printed will increase immediately.
Okay, how many ALM parts are in flight already? Can you make a guesstimate?
That's really difficult to answer. So on the 350 we have one plastic part and some titanium parts. So each aircraft, I would say 3-4 parts maybe. And on the older programs like A320 and A330, we have mainly plastic parts in the cabin. I would say roughly about 4 or 5 parts per aircraft. Not so much. Okay. So we are at the start, but we are using it in the series now. And we are ready to increase the number of parts, which is for sure a step-by-step approach.
Okay, and then one last question is: do you use both DED and Metal PBF processes in the Bremen facility? Which one is more in line with your current manufacturing requirements?
So if someone can explain to me what does it mean, DED and PBF?
It's a question that comes from 3D PDB. Yes.
Ah. At the top.
At the top.
You have no mic.
Yes, we have.
But to answer the question, in principle, I'm using no 3D printer in Bremen because we are using our suppliers to producing the parts for us. We have a proto space where we have a 3D printer to test parts and to make models and to simulate. but on our own we are not producing the parts so far. But about the process, maybe DED?
It's metal deposition.
Sorry? Yeah, E-beam, okay.
So the question was basically if like the metal deposition technology has a much higher deposition rate and the powder technology is much more precise, and that was kind of what I was getting to. Do you need the geometry or the dimensions?
So we are using both technologies, but for the qualification so far we are focusing on the powder bed.
Thanks.
Okay, and then I will pick one last question that didn't win, but that I would like to have the answer on, and that is, what is the typical time between design and final manufacturing, including certification?
So I will not answer it for common parts, because then my boss will challenge me, because for sure we need to reduce the time between design and production. But for the 3D printed parts, it's very short, because we have a special task force who's working on it. And let's say starting from the idea to get delivered a part can be in a period of 3 months. And if you need to qualify it, you need additional 3 or 6 months. It depends on the part and on the class where you need to qualify it.
Okay, thank you. Well, ladies and gentlemen, thank you very much for your interaction. Dr. André Walter, thanks for your...
Thanks a lot for the questions.